They told us the universe was built to last, but that was never true. Everything you see, stars, galaxies, even our sun, is slowly being used up. Not in the distant future, but right now, without stopping. Today we uncover entropy, the law turning the entire universe into a countdown. Now, let's begin. Right now, as you listen this, the sun is destroying itself. Not slowly, not metaphorically. 4 million tons of mass gone every single second, converted into the light that makes life on this planet possible. That number is not an estimate. It is a measurement. 4 million tons per second around the clock, without pause, without any mechanism to recover what was lost. The energy reaching your skin on a clear afternoon is the direct product of irreversible destruction happening 93 million miles away in real time. That fact alone should be unsettling. It is not because the sun looks permanent. It has looked permanent every morning of every human life ever lived. The problem is not with the Sunday. The problem is with the timescale. Human intuition is built to process. We feel minutes. We understand years. We can stretch with effort to decades and centuries. But the sun has been burning for 4.6 billion years and has roughly 5 billion years remaining, a span so far outside the range of lived experience that the brain quietly files it under effectively forever and moves on. That filing is a mistake, and it is the foundational mistake behind everything that follows. The sun is not special. Across the observable universe, 2 trillion galaxies, each containing hundreds of billions of stars. Every single one of those stars is doing the same thing. Each one is a nuclear furnace consuming a finite, non-renewable fuel supply that was fixed at the moment of its formation. None of them are refueling. None of them have a mechanism to reverse the process. The universe is not a system in balance. It is a system in controlled, one-directional collapse, and the stars we look at with wonder are not signs of vitality. They are the visible evidence of that collapse in progress. This is not poetry. This is the second law of thermodynamics, the most battle-tested principle in all of physics. Every process in the universe increases the total disorder of the system. Energy moves from concentrated, usable forms to diffuse, unusable forms. Heat flows from hot to cold, never the reverse. The law has no confirmed exceptions in the entire recorded history of science, not one. Not in a laboratory, not in a particle accelerator, not in any observation of any astronomical object anywhere. It applies at every scale without negotiation, and the universe as a whole is the largest closed system that exists. The conclusion follows by arithmetic. The universe is running down, has always been running down, will continue running down until there is nothing left to run. What makes this genuinely difficult to sit with is not the scale, it is the irreversibility. Consider a simple image. A glass falls from a table and shatters on the floor. Every physical law governing that event, gravity, momentum, the transfer of energy between colliding surfaces, is mathematically reversible. The equations work equally well in both directions. And yet no one has ever watched shards of glass leap off the floor, assemble themselves into a perfect drinking vessel, and land upright on the table. The reason is entropy. The shattered state is astronomically more probable than the intact state. Time at the physical level runs in the direction of increasing disorder because that is the direction of increasing probability. The arrow of time is not a feature of the fundamental equations. It is a statistical consequence of entropy. The universe began somehow in a state of extraordinary order. That order is being spent. Time runs forward because entropy runs forward. And entropy runs forward because there is nowhere else to go. Here is the number that Roger Penrose calculated, and it is important to understand that Penrose is not a fringe figure. He is one of the most rigorous mathematical physicists alive, a Nobel laureate, a collaborator of Stephen Hawking. He calculated the probability that the universe began in a state of order as low as it actually did. The answer is 1 in 10 to the power of 10 to the power of 123, not 10 to the 123rd. 10 to the power of a number that is itself 10 to the 123rd. The total number of atoms in the observable universe is approximately 10 to the 80. That number, vast enough to be meaningless to human intuition, does not come close to describing the denominator of Penrose's probability. There is no language in standard mathematics to convey how improbable the initial condition of the universe was. Penrose did not present this calculation as a triumph. He presented it as a crisis evidence that something fundamental about the origin of the universe remains completely outside current physical understanding. But here is the part that inverts everything: that same improbable, extraordinary, nearly impossible initial order is the only reason anything exists at all. Stars form because gravity pulls matter toward density gradients. Gradients that only exist because the early universe was ordered enough to have them. Chemistry works because atoms bond in structured ways. Structure's only possible because the cooling of the early universe followed a precise sequence enabled by low entropy. Life exists because it can extract usable energy from its environment. Usable energy that exists only because the universe still has order left to spend. Every thought, every structure, every process that has ever occurred in the history of the cosmos is a downstream consequence of that single improbable starting condition. And the same law that made all of it possible guarantees all of it ends. Now, place humanity in this timeline honestly. The universe is approximately 13.8 billion years old. The smallest, most fuel-efficient stars, red dwarfs with a fraction of the sun's mass, will burn steadily for 10 trillion years. That is roughly 700 times the current age of the universe. And red dwarfs are not the end of the story. After the last star goes dark, black holes will dominate the universe for timescales that make stellar lifetimes look instantaneous. The complete evaporation of the largest black holes through Hawking radiation takes an estimated 10 to the power of 100 years. If the entire future lifespan of the universe were compressed into a single calendar year, the whole of human civilization, from the first controlled fire to the launch of space telescopes, would occupy less than 1/10,000th of a trillionth of the first second of January. First. Not the first day, not the first hour. A sliver of time so small it has no name in any human language. The universe has barely started. The stars visible tonight are an early chapter phenomenon, and the story ends in a darkness so complete and so permanent that the word darkness is inadequate, because darkness implies the potential for light. What waits at the end of entropy is the absence of any process, any gradient, any event of any kind. Physicists call it heat death. It is the condition where nothing further can happen because nothing remains to drive anything forward. That is one ending, the one physicists currently consider most probable. There are two others. And unlike heat death, which arrives slowly over timescales that dwarf imagination, one of them could tear the universe apart before entropy ever gets the chance. The other suggests the universe does not end at all, but has been ending and beginning in an endless cycle that makes the question of the final state meaningless. Which one is correct depends entirely on the nature of a force that constitutes 68% of everything in the universe. A force with a name, a measured effect, and a completely unknown physical identity. If the second law of thermodynamics is absolute and without exception, why did the universe begin in a state of such extreme improbable order rather than starting already in chaos? And does current physics have any answer to that question? The answer requires understanding entropy not as an abstract to thermodynamic quantity, but as the single mechanism governing everything from why galaxies form to why time refuses to run backwards. And once that mechanism is clear, the question of which ending awaits the universe stops being philosophical entirely. Most people encounter entropy as a word meaning disorder. That definition is not wrong. It is incomplete in a way that obscures the actual mechanism. Entropy is a measure of how many different ways a system can be arranged while still looking the same from the outside. A room described as tidy corresponds to a very small number of arrangements: books on shelves, surfaces, clear objects in designated places. A room described as messy corresponds to an astronomically larger number of arrangements. Books can be on the floor in countless configurations, objects scattered in any of a near infinite number of positions. When you leave a tidy room unattended, it does not spontaneously become tidier. It drifts toward mess not because some force is pushing it toward chaos, but because the number of messy arrangements overwhelms the number of tidy ones by a factor that makes lottery odds look favorable. The universe operates on the same principle at every scale simultaneously. Take a 500,000 dong note and burn it. The energy content of that note does not disappear. It disperses into heat radiating outward through the air into light, into the kinetic energy of rising smoke particles. Total energy is conserved exactly as physics demands, but the energy that was concentrated, structured, and available to do useful work is now diffused across an enormous volume of space in a form that can no longer drive any directed process. You cannot collect that dispersed heat and reconstruct the note. The information about the note's structure has not been destroyed in principle. It is encoded somewhere in the positions and velocities of every particle involved in the combustion, but it has been distributed across such a vast number of degrees of freedom that recovering it is not merely difficult, it is for all practical purposes of the physical universe impossible. This is entropy, not disorder in the aesthetic sense. The irreversible dispersal of concentrated structure into states too diffuse to recover. Every star in the universe is that burning note at a scale of 10 to the 29th kilograms. The Sun fuses hydrogen nuclei into helium in its core, releasing energy that was locked in the mass difference between reactants and products. That energy travels outward through 8 minutes of space and arrives at Earth as usable concentrated radiation. It drives photosynthesis, weather, ocean currents, the entire biosphere. Then it is absorbed, converted, degraded, and eventually radiated back into space as lower energy infrared, slightly warmer than the cosmic background, slightly more diffuse, slightly less useful. Every step of that chain increases entropy. The original concentrated nuclear energy becomes progressively more spread out, more equalized, more irretrievable. Multiply this by every star in every galaxy running continuously for billions of years, and the direction of the universe becomes impossible to misread. Here is the apparent paradox that requires addressing directly, because it is the objection that always arises if entropy always increases. How does complexity appear? How do galaxies form from diffuse gas clouds? How do planets coalesce from debris disks? How does life, which is arguably the most ordered complex, improbable structure in the known universe, emerge from chemistry? The answer is that entropy is a global accounting, not a local prohibition. A refrigerator makes its interior colder, a local decrease in entropy order imposed on the contents. But the refrigerator releases more heat into the room than it extracts from the interior. The total entropy of the room plus refrigerator increases. The local order is purchased at the cost of greater global disorder. The same logic applies everywhere. Gravity pulls diffuse gas into stars, creating order, but the gravitational collapse releases enormous amounts of energy into the surrounding space. A net entropy increase globally despite local structure formation. Life extracts order from its environment with extraordinary efficiency, but it also generates heat exhales, high entropy waste products, and ultimately returns all of its borrowed order to the environment at death. Every island of complexity in the universe is surrounded by a sea of increasing entropy that it is actively generating as the price of its own existence. This is the fact that makes every civilization, every philosophy, every framework of meaning built on the assumption of a universe trending toward greater complexity and higher purpose run directly into a physical wall. Not a metaphorical wall, a thermodynamic one. Humanity spent several thousand years constructing worldviews in which the cosmos has a direction toward order, toward meaning, toward some destination that justifies the journey. Various traditions arrived at different versions of this assumption, but the assumption itself was nearly universal. Progress, evolution, spiritual development, cosmic purpose. All of them require a universe that is at some level going somewhere worth going. The second law does not accommodate that requirement. It has one direction and one destination, and neither is optional. It is possibly the most philosophically destabilizing scientific result in history, and it arrived not through a dramatic experiment or a revolutionary theory, but through engineers in the 19th century, trying to build more efficient steam engines. The universe's death sentence was written in a factory between calculations about pistons and pressure gauges. There is something almost deliberately anticlimactic about that. But the law itself is not anticlimactic, because the second law understood fully does not merely predict the eventual death of the universe. It explains why time has a direction at all. At the fundamental level, the equations of physics, quantum mechanics, general relativity, electromagnetism are time symmetric. Run the equations forward or backward, they work equally well. There is no mathematical reason at the level of individual particle interactions why time could not flow in reverse. And yet it does not. The past is fixed. The future is open. Cause precedes effect. Memory runs one direction. Aging runs one direction. All of that, the entire experience structure of time, traces back to entropy. Time runs forward because entropy runs forward. Because the universe began in a state of extraordinary order and is moving irreversibly toward a state of maximum disorder. The arrow of time is the arrow of entropy. They are the same thing, which returns inevitably to the question of how the universe began in that extraordinary state, because the second law makes the initial condition of the universe not just unusual, but in the most precise statistical sense, the most improbable event in the history of improbable events. If entropy always increases globally, while allowing local pockets of order to form what is the ultimate limit on how complex those local structures can become, and is there a point at which complexity itself accelerates entropy production, rather than resisting it? The answer traces back to how the universe began, and what happened in the first fraction of a trillionth of a trillionth of a trillionth of a second of existence determined everything about how it ends. Every popular image of the Big Bang is wrong. The image is always the same: a point, a flash, an expanding fireball blasting outward into surrounding darkness. It is dramatic, it is intuitive, it maps cleanly onto every explosion a human being has ever witnessed. And it is wrong in a way that is not a minor technical correction. It is wrong at the level of the conceptual framework, and the actual picture is considerably stranger than any explosion. The Big Bang was not an explosion in space. It was an expansion of space itself. The distinction matters more than it might initially appear. An explosion occurs inside an existing space. It has a center, a direction of propagation, a boundary between where the explosion is and where it is not. The Big Bang had none of these features. There was no pre-existing space for it to explode into. There was no center from which matter flew outward. There was no edge where the expansion stopped and empty space began. Space itself, the fabric in which matter and energy exist, came into being and expanded everywhere simultaneously. The question, where did the Big Bang happen, is not a question that lacks a good answer. It is a question that is malformed at the conceptual level in the same way that asking what is north of the North Pole is malformed. North is a direction defined relative to the Earth's rotational axis. At the North Pole, you are standing at the point the axis defines, and the concept of further north ceases to have geometric meaning. Similarly, the Big Bang did not happen at a location within space. It was the event from which space itself originated. There is no position on any map you could point to and say there. Every point in the universe was the center of the Big Bang, including the exact location where you are sitting now. This is not a poetic statement. It is a geometric consequence of how space expansion works. If the universe is expanding everywhere simultaneously, every point moving away from every other point like dots drawn on the surface of an inflating balloon, then every point is equally the origin. There is no privileged location. The Milky Way is not closer to the center of the Big Bang than a galaxy 10 billion light-years away. The concept of closer to the center has no referent. What happened at the moment of the Big Bang, more precisely in the earliest moments after it, is a question physics can approach only to a limit and then fall silent. That limit is called the Planck time, approximately 10 to the negative 43 seconds after the beginning. Before that threshold, the known laws of physics, general relativity, describing gravity, quantum mechanics, describing everything else, break down simultaneously. They produce infinities where they should produce numbers. They contradict each other in ways that have no resolution within current theory. The state of the universe before Planck time is not merely unknown. It is currently unknowable with any existing or foreseeable theoretical framework. The singularity, the term for the initial state of infinite density and temperature, is not a physical description of what actually existed. It is the mathematical signal that a theory has been pushed beyond its domain of validity. When an equation outputs infinity, the correct interpretation is not infinity existed. The correct interpretation is this equation does not apply here. The singularity marks the edge of what current physics can describe, not the beginning of what physically occurred. All of that, however, is not the most important thing about the Big Bang for the purposes of this story. The most important thing, The detail that connects the origin of the universe directly to the question of its ending is this. Whatever process produced the universe did so with entropy at an extraordinarily, almost impossibly low value. Think about what that means concretely. Imagine arriving at a hotel room to find it in a state of absolute perfection, not merely clean but arranged with a precision that goes beyond any housekeeping standard. Every molecule of air distributed in the exact configuration that maximizes the room's potential for future change. Every object positioned to enable the maximum number of subsequent events. The question a physicist would ask upon walking in is not why is this room going to get messy? Entropy guarantees the answer to that. The question is, who arranged this room and how and why before I arrived? That is the question the Big Bang leaves on the table. The universe arrived from whatever process preceded or produced it in a state of extraordinary, improbable, structurally specific low entropy. Not randomly low, precisely, specifically, low in ways that enabled the formation of structure, the slight density variations in the early universe that gravity would later amplify into filaments, galaxies, stars, and everything that followed. The low entropy was not generic tidiness. It was the particular kind of low entropy that makes complexity possible downstream. Roger Penrose quantified the improbability of this initial state, and the result has never been refuted or superseded. The probability of a universe beginning with entropy as low as ours, selected at random from all possible initial states of equivalent energy, is 1 in 10 to the power of 10 to the power of 123. Writing out that denominator would require more space than the observable universe contains. The number is not large in the way that astronomical distances are large quantities that dwarf human experience, but remain finite and comprehensible in principle. This number is in a category that has no meaningful analogy. It sits at the edge of what mathematics can express and what the human mind can gesture toward without fully grasping. Penrose did not calculate this to marvel at it. He calculated it to identify it as the central unsolved problem in cosmology. A universe beginning in a state that improbable is not the product of chance, statistically it cannot be. Something about the process that produced the universe selected for that initial condition. Current physics has no agreed explanation for what that something was, and yet without it nothing follows. No stars, no chemistry, no planets, no biology, no observers to notice the improbability. The low entropy of the Big Bang is not background detail. It is the load-bearing structure underneath every event that has ever occurred. The universe began in an extraordinary state of order. The second law ensures it has been spending that order ever since. And the rate and manner in which that order is spent, whether it runs down gradually over 10 to the 100 years, or gets torn apart violently in a fraction of that time, or collapses back on itself before entropy even finishes its work, depends on physics that is still being measured, still being contested, and still capable of surprising the people doing the measuring. If low initial entropy was the necessary condition for life to exist, and current physics cannot explain what produced that condition does, that gap represents a temporary limit of current theory, or something more fundamental about what science can and cannot answer. Science does not answer that question, but it has uncovered something considerably more unsettling in the process of trying. Right now, space is expanding faster than light, and the majority of the universe has already passed permanently beyond our reach. The speed of light is 299,792 kilometers per second. That number is not merely a property of light. It is the absolute speed limit of information in the universe, the maximum rate at which any signal, any influence, any causal connection can propagate through space. Nothing with mass can reach it. Nothing carrying information can exceed it. It is baked into the structure of space-time at a level more fundamental than any material property. This limit is why the night sky is a time machine. The light arriving from the Andromeda galaxy left its source 2.5 million years ago. The light from the most distant objects visible to current telescopes has been traveling for over 13 billion years. Looking outward in space is without exception looking backward in time, because light takes time to cross distance, and the universe is old enough and large enough that the time involved is cosmologically significant. All of that is the familiar part. Here is where it becomes genuinely strange. Space itself is not bound by the speed of light. The speed limit applies to objects and signals moving through space. Space expanding is a different category of event entirely. It is not motion through a background, it is the stretching of the background itself. And that stretching has no speed limit imposed by relativity. At distances beyond a certain threshold, currently calculated at approximately 14 billion light-years, space between here and any given point is expanding faster than light could cross it. This does not mean those regions are unreachable because travel is too slow. It means that even a signal traveling at the maximum possible speed in a perfectly straight line toward us is losing ground. The space between the source and the destination is growing faster than the signal can traverse it. The signal will never arrive. The boundary defined by this condition is called the cosmological event horizon. Anything beyond it is causally disconnected from us, not in the future, not with better technology, not with any conceivable development in physics. Permanently. The disconnection is written into the geometry of expanding spacetime and cannot be reversed by any mechanism operating within that spacetime. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years. That number is larger than the 13.8 billion light-years one might expect from the age of the universe, because space has been expanding throughout the journey of that light, stretching the distances involved. But the cosmological event horizon, the boundary beyond which no future signal can ever reach us, sits at approximately 16 billion light-years. Everything between 16 billion and 46 billion light-years is visible now, but only because the light left long enough ago when those regions were closer. New light from those regions emitted today will never reach us. The horizon is not static. Dark energy, the force driving accelerated expansion, is pushing it inward in practical terms. With each passing year, more galaxies cross the threshold from will eventually be unreachable to already unreachable. This is happening continuously in real time to real objects. Thousands of billions of galaxies are currently on the far side of that line. Their light is en route, some of it having travelled for billions of years, and it will never complete the journey. Not because anything stopped it, because the space it needs to cross keeps growing faster than it can move. This loss is not recoverable. There is no observation, no instrument, no future advance in astronomy that will restore access to those regions. They are gone from the causal structure of our universe, as completely as if they had never existed. For all purposes that involve any interaction with us, they effectively have not. The implications compound in a direction that is easy to overlook. 2 trillion years from now, a number so large it renders all of human history negligible. The galaxies currently making up the observable universe will have receded beyond the event horizon entirely. With one exception, the galaxies, gravitationally bound to the local group, the small cluster containing the Milky Way Andromeda, and roughly 60 smaller companions. Those galaxies will eventually merge into a single large elliptical galaxy. Every other galaxy in the universe, the hundreds of billions of them, visible in deep field images from current telescopes, will have vanished beyond the horizon, their light redshifted to wavelengths too long to detect their existence, inaccessible by any physical means. Any civilization existing in that merged galaxy 2 trillion years from now would look out at a universe containing a single island of stars, surrounded by absolute featureless darkness. No other galaxies, no redshift surveys showing cosmic expansion, no background radiation bright enough to detect with reasonable instruments. They would have every observational reason to conclude they lived in a static, eternal, isolated universe and no way to discover otherwise. They would be wrong about nearly everything fundamental, and they would have no way to know it. The cosmological knowledge that humanity currently possesses, the expanding universe, the cosmic microwave background, the large-scale structure of galaxy filaments and voids, is available only because we exist in this specific narrow window of cosmic time, early enough that the evidence of the Big Bang is still detectable, late enough to have developed the technology to measure it. The window is closing. Not on a human timescale, but it is closing, and what lies on the other side of it is a universe that has erased the evidence of its own origin. This is not a hypothetical concern about distant civilizations. It is a statement about the relationship between physical reality and observational access to it. The universe does not preserve its history in a form that remains readable indefinitely. Evidence decays. Signals redshift into noise. Horizons advance. The story of how the universe began is written in light that is currently in transit, and once that light is gone, the story goes with it permanently and irrecoverably. Humanity is in this precise sense, in a race against the expanding horizon. Every observation made now, every measurement of the cosmic microwave background, every survey of galaxy distribution, every calculation of the universe's expansion history, all of it is work that becomes progressively less possible as time advances and at some point becomes impossible entirely. The maps being built today are the only maps that will ever be built. No future generation, however advanced, will have access to the raw data that makes them possible. If a civilization arising 5 trillion years from now in the Milky Way would have no observational access to evidence of the Big Bang, the cosmic microwave background, or any other galaxy, could they independently discover that the universe had a beginning at all? The answer is no, and that fact raises a deeply unsettling question about what the universe is currently concealing from us, hidden not in the future, but buried in its own past. In 1998, 2 independent research teams set out to measure how fast the universe was slowing down. That phrasing is deliberate. The assumption built into their research design, the assumption built into virtually every cosmological model at the time, was that the expansion of the universe was decelerating. The Big Bang had set everything in motion. Gravity had been pulling matter back together ever since. The only open question was whether there was enough matter to eventually reverse the expansion entirely, or whether the universe would simply coast outward forever at a gradually diminishing rate. Deceleration was not a hypothesis being tested. It was the background assumption against which the measurement was being made. Both teams were using Type Ia supernovae as their measuring instruments. These stellar explosions have a property that makes them extraordinarily useful for cosmology. They detonate at a consistent peak luminosity, reliably enough that comparing how bright they appear against how bright they should be yields a precise distance measurement. Map enough of them at different distances, and you can reconstruct the expansion history of the universe, how fast it was expanding, at different points in cosmic time. The results from both teams arrived independently. Both sets of data pointed in the same direction. Neither team published immediately because neither team believed their own numbers. The universe was not decelerating. It was accelerating. The expansion of space was speeding up. This result violated not just the prevailing model but the foundational physical intuition underlying it. Gravity attracts. It pulls matter together, slows expansion, works against separation. Every force known to physics at that time acted to decelerate the universe's expansion at cosmological scales. For the expansion to be accelerating, something had to be pushing. Not matter, not radiation, not any known field or particle. Something with the property of exerting a repulsive effect on space itself, uniformly distributed across the entire universe, growing stronger in its total effect as space expanded and created more volume for it to act within. Nothing in the existing toolkit of physics described this. Nothing came close. The 2 teams, the High Z Supernova Search Team and the Supernova Cosmology Project, shared the Nobel Prize in Physics in 2011. The discovery is confirmed science. The acceleration is real, measured now by multiple independent methods converging on the same conclusion. But the confirmation of the observation did nothing to explain the mechanism. The name given to whatever is causing this dark energy was never intended as a description. It was a placeholder, an admission formalized in 2 words that something constituting the dominant component of the universe had been discovered and was completely, utterly not understood. The word dark in physics does not carry the connotations it carries in everyday language. It does not mean sinister, mysterious in a romantic sense, or hidden by shadow. It means undetected by any form of electromagnetic radiation, invisible not because it absorbs light, but because it does not interact with light at all. Dark matter is dark in this sense. So is dark energy. The naming convention is precise and in context brutal. These things are dark because every instrument humanity has built to observe the universe operates on electromagnetic interactions, and these components of reality simply do not participate in those interactions. They are present everywhere. They dominate the universe by proportion, and they are invisible to every direct detection method available. The proportions measured with current precision are as follows. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter constitutes approximately 27%. Everything else, every star, every planet, every gas cloud, every black hole, every galaxy visible in every telescope image ever taken, every atom in every living organism on Earth, constitutes approximately 5%. Modern physics has a detailed, tested, extraordinarily precise understanding of that 5%. The standard model of particle physics describes its behavior with an accuracy that has been experimentally confirmed to more decimal places than almost any other scientific theory. General relativity describes how that 5% curves spacetime with a precision that now underpins GPS satellite calibration. The physics of the visible universe is arguably the greatest intellectual achievement in human history. It covers 5% of what exists. The remaining 95% carries labels. Dark matter, a label on a gravitational effect, whose source has never been directly detected despite decades of increasingly sensitive experiments designed specifically to find it. Dark energy, a label on an acceleration whose mechanism has no agreed physical explanation. These are not names for understood phenomena. They are names for gaps boundaries where the map of knowledge ends and uncharted territory begins, dressed in the vocabulary of discovery to make the ignorance easier to discuss. Albert Einstein introduced a term into his field equations of general relativity in 1917 called the cosmological constant, represented by the Greek letter lambda. He added it specifically to counteract gravity and produce a static universe, because the prevailing assumption at the time was that the universe was neither expanding nor contracting. When Edwin Hubble's observations in 1929 demonstrated that the universe was in fact expanding, Einstein called the cosmological constant his greatest mistake and removed it from his equations. The story of that self-correction became one of the most frequently repeated anecdotes in the history of science. After 1998, the cosmological constant was reinstated. The accelerating expansion of the universe requires exactly the kind of term Einstein introduced: a constant energy density associated with empty space itself, pushing outward uniformly across the entire universe. The mathematics he wrote in 1917 for entirely wrong reasons turned out to describe the right phenomenon for reasons he never considered and would not have predicted. The cosmological constant, if dark energy is indeed constant, if its energy density per unit volume of space does not change over time, leads to one specific future for the universe. Expansion continues, accelerates gradually, and the universe ends in the cold, dark, maximally entropic state described by thermodynamics. A slow death, inevitable but distant. But the cosmological constant is an assumption, not a measurement. Dark energy could be something other than a fixed property of space. It could be a dynamic field whose energy density changes over time. It could weaken potentially, allowing gravity to eventually reverse the expansion. It could stay constant, or it could strengthen its energy density, increasing as the universe expands, its repulsive effect growing without limit. The parameter physicists use to characterize dark energy's behavior is called W, the ratio of its pressure to its energy density. If W equals -1, exactly dark energy is constant. If W is greater than -1, it weakens over time. If W is less than -1, if dark energy is what some theorists call phantom energy, its density increases as space expands, and its effect compounds without ceiling. Current measurements from surveys including the Dark Energy Spectroscopic Instrument, which released its first major results in 2024, suggest W may not be exactly -1. The signal is not definitive. The uncertainty is significant. But the data does not exclude the possibility that dark energy is evolving, and if it is evolving in the direction of increasing strength, the timeline of the universe changes from a slow thermodynamic fade to something categorically different. Not a cooling, not a gradual dispersal into darkness, a tearing. If dark energy increases in strength over time, rather than remaining constant, what is the mechanism by which it would overcome not just the expansion of space between galaxies, but the gravitational and electromagnetic forces binding matter, together at progressively smaller scales? That question has a name: the Big Rip, and it describes a scenario in which everything from superclusters of galaxies down to individual protons is torn apart by the structure of space itself. If dark energy is what the simplest interpretation of current data suggests, a fixed property of space, constant in its energy density, neither strengthening nor weakening as the universe expands, then the future of the universe is already written, not in broad strokes, in specific calculable stages with timescales that can be estimated from known physics. The ending is not dramatic. It is the opposite of dramatic. It is the most thorough and irreversible quietude that the laws of thermodynamics can produce. This scenario has a name: the Big Freeze. It is currently the most widely supported outcome among cosmologists, not because it is the most interesting, but because it is the most consistent with the available evidence. And understanding it in sequence, stage by stage, across timescales that make the current age of the universe look like an opening footnote, is the only way to grasp what thermodynamic death actually means at its full scale. The first stage is already underway. Star formation across the universe is declining. The rate at which gas clouds collapse into new stars peaked roughly 10 billion years ago and has been falling ever since. The universe is not yet dark, but the trend is established and irreversible. The raw material for new stars, cold hydrogen gas, dense enough to collapse under gravity, is being consumed faster than any process replenishes it. In approximately 100 trillion years, the last star capable of sustaining nuclear fusion will exhaust its fuel and go dark. 100 trillion years. The current age of the universe is 13.8 billion years. 100 trillion is roughly 7,000 times longer than the universe has existed so far, and it is the first line of the final chapter. The transition will not be gradual in the way that word suggests. It follows a thermodynamic schedule. The most massive, brightest stars burn through their fuel in millions of years and are already long gone. Mid-range stars like the Sun last billions of years. The smallest red dwarf stars, with perhaps a tenth the mass of the Sun, burning hydrogen so conservatively that they never leave the main sequence, persist for 10 trillion years or more. These dim, cool, barely visible embers will be the last fires in the universe. When they finally exhaust their cores, the era of stars will be over completely. Not fading, over. What follows is the degenerate era, a period dominated by the cold remnants of stellar evolution. White dwarfs the dense crystallized cores left behind when sun-like stars exhaust their outer layers. Neutron stars, the collapsed remnants of more massive stars, city-sized objects with the density of atomic nuclei. And black holes, the endpoints of the most massive stellar deaths regions, where gravity has overwhelmed every other force in space-time, curves in on itself without return. These objects do not burn. They do not generate energy through any active process. They simply persist, radiating residual heat into an increasingly cold surrounding universe, cooling toward absolute zero, across timescales of 10 to the power of 15 years, 10 to the power of 20 years longer. The universe during this era is dark, cold, and nearly silent, populated by objects that are the thermodynamic ghosts of a stellar epoch already billions of years in the past. Black holes, however, are not permanent. This is the contribution of Stephen Hawking, published in 1974, that transformed the theoretical understanding of black hole physics. Through a quantum mechanical process occurring at the event horizon, the boundary beyond which nothing escapes, black holes slowly emit radiation and lose mass. The mechanism involves quantum fluctuations at the horizon boundary, producing pairs of particles, one of which escapes while the other falls inward, resulting in a net energy loss from the black hole over time. The process is extraordinarily slow. For stellar mass black holes, the evaporation timescale is approximately 10 to the power of 67 years. For the supermassive black holes anchoring the centers of galaxies objects, with masses millions or billions of times that of the Sun, the timescale extends to approximately 10 to the power of 100 years. Hawking radiation has never been directly observed. The emission from any black hole accessible to current instruments is so faint as to be completely undetectable against the background of the cosmic microwave background radiation. But the theoretical basis is robust, grounded in well-established quantum field theory, applied to curved spacetime, and the physics community treats the eventual evaporation of black holes as a reliable prediction rather than a speculative claim. After the last black hole evaporates after 10, to the power of 100 years have elapsed, what remains is a universe containing nothing capable of any further organized process. No mass concentrations, no temperature gradients, no usable energy of any kind. Only an extremely dilute gas of the lowest energy particles, photons redshifted to wavelengths longer than the observable universe, neutrinos too cold to interact with anything, and scattered electrons and positrons drifting through a space that continues to expand, growing colder and emptier with every passing moment. Temperature in this final state approaches absolute zero asymptotically. The universe never quite reaches it. Absolute zero is a limit, not a state any physical system achieves. But the distinction between approaching absolute zero for 10 to the power of 100 years and reaching absolute zero is for all physical purposes a distinction without a difference. No process can occur, no event can happen, no information can be exchanged. The universe has reached maximum entropy, the state in which every possible configuration is equally probable, which means no configuration is distinguishable from any other, which means nothing further can change in any meaningful sense. Physicists call this state heat death. The naming is a small masterpiece of misdirection. Heat death occurs at a temperature indistinguishable from absolute zero, the complete absence of thermal energy. The word heat in the name refers not to the final temperature, but to the thermodynamic concept of heat as a form of energy transfer. When no temperature gradients remain to drive energy flow, heat transfer ceases. The universe is thermally dead, not because it is hot, but because it is so uniformly cold that no thermal process can ever occur again. The physics community named the ultimate cold death of all existence after heat. No marketing department would have approved this. There is one variable that could accelerate the timeline significantly. Several theoretical frameworks, including certain versions of grand unified theories, predict that protons are not stable over infinite time. If protons decay, they do so with a half-life estimated at somewhere above 10 to the power of 34 years, which is the current experimental lower bound from proton decay searches. If proton decay is real, it eliminates white dwarfs and neutron stars on a timescale of roughly 10 to the power of 40 years, well before Hawking radiation finishes its work on the black holes. The matter content of the universe dissolves into lighter particles and radiation earlier than stellar remnant cooling would dictate. The sequence of the degenerate era changes, but the destination does not. The destination is always the same: maximum entropy, no gradients, no events. No time distinguishable from any other time, because time's arrow, the direction defined by increasing entropy, has nowhere left to point. If proton decay is confirmed experimentally, with a half-life near the current theoretical lower bound, it would eliminate all atomic matter within 10 to the power of 40 years, well before black hole evaporation completes. Does this change the fundamental character of the Big Freeze endpoint, or only the route by which the universe arrives there? But the Big Freeze assumes dark energy is constant. If it is not constant, if it is increasing, then the universe does not die in silence, but in the tearing of space itself. The Big Freeze is a death by exhaustion. The universe runs through its usable energy. Entropy reaches its maximum and everything stops. It is long, cold, and thermodynamically inevitable, but it is, in a strange sense, a natural death. The kind of ending that follows logically from the beginning, the middle chapter playing out to its conclusion without any external violence. The Big Rip is categorically different. It is not entropy completing its work. It is the structure of space-time itself, failing every force that holds matter together, overcome in sequence by an expanding repulsive energy that grows without limit until there is nothing left to tear. The mechanism begins with the same observation as the Big Freeze. Dark energy is driving accelerated expansion. But where the Big Freeze assumes the energy density of dark energy remains constant as space expands, the Big Rip requires what theorists call phantom energy, a form of dark energy whose density increases as the volume of space increases. The more space expands, the more dark energy there is per unit volume, which drives further expansion, which creates more dark energy in a compounding feedback with no natural ceiling. The parameter W, the ratio of dark energy's pressure to its energy density, governs which scenario applies. A value of exactly -1 corresponds to a cosmological constant producing the Big Freeze trajectory. A value greater than -1 allows for a weakening dark energy that eventually permits the Big Crunch. A value less than -1, phantom energy, leads to the Big Rip. Current measurements, including the first major data release from the Dark Energy Spectroscopic Instrument in 2024, place W near -1, but with uncertainties that do not yet exclude values below it. The Euclid satellite, launched in 2023 and currently operational, is accumulating data that will sharpen these constraints considerably over the coming years. If W is less than -1 and the Big Rip is the correct trajectory, the timeline of destruction can be calculated from the value of W and the current expansion rate. Estimates range from approximately 20 billion to 200 billion years in the future, depending on how far below -1 the true value of W falls. The uncertainty is large. The physics, once the value of W is fixed, is deterministic. The sequence of destruction follows a precise logic. The repulsive effect of dark energy overcomes forces in order of their strength from weakest to strongest. Gravity is the weakest of the four fundamental forces by an enormous margin, a fact that is easy to forget because it is the dominant force at astronomical scales where the other forces have already cancelled out. At cosmological scales, dark energy already competes with gravity. As phantom energy density increases, gravity loses first. The large-scale structure of the universe, the web of galaxy filaments and superclusters assembled over billions of years, begins to pull apart. Superclusters dissolve. Galaxy clusters that have been gravitationally bound for most of cosmic history separate into their constituent galaxies. This begins roughly a few billion years before the final moment. Individual galaxies follow. The gravitational binding that holds a galaxy's stars in their collective orbits is stronger than the filament-scale gravity holding superclusters together, so it holds longer but not indefinitely, a few 100 million years before the end galaxies begin to disperse. Stars that have shared a gravitational system for billions of years drift apart on trajectories they will never complete. As the endpoint approaches, the timescales compress. A few months before the final moment, solar systems dissolve planets released from their orbits around stars. Weeks later, the stars themselves are no longer gravitationally self-bound. Days later, planets, if any remain structurally intact, are torn apart by the expanding repulsive field acting differentially across their volume. The electromagnetic force holding atoms into molecules and molecules into bulk matter is overcome. Chemistry ends. In the final seconds, the strong nuclear force, the strongest of the four fundamental forces, the binding that holds quarks together inside protons and neutrons, is overwhelmed. Atomic nuclei disintegrate. Protons and neutrons dissolve into their constituent quarks. The last stable structures in the universe come apart. At the final moment, space-time itself reaches a singularity. Not a point singularity, like the one at the center of a black hole, a universal singularity occurring simultaneously at every location in space. The geometry of space-time breaks down everywhere at once. The expansion rate becomes infinite in finite time. The question of what exists after that moment, what after even means when space-time has ceased to exist as a coherent structure, has no answer in any current physical framework. It is not that the answer is unknown. It is that the question has no well-formed meaning once space-time is no longer a valid mathematical object. There is a way to make the Big Rip viscerally comprehensible without losing its physical accuracy. Think of space-time not as a fixed arena in which events occur, but as a medium with structural integrity. The way a soap bubble has structural integrity, the bubble can expand, it can deform, but its surface has a tension that maintains it as a coherent object. In the Big Rip, there is no external tension maintaining space-time. There is only the repulsive energy embedded within it, growing without limit, stretching the medium past any analogue of a breaking point, except that the medium is everything, and breaking it does not produce pieces. It produces the end of the conditions under which the concept of pieces is meaningful. What makes the Big Rip the most unsettling of the three major scenarios is not its violence, it is its finality. Big Freeze allows for the theoretical possibility, however. Remote and physically constrained, that complexity of some kind persists in some form for extraordinarily long periods. The Big Rip allows for nothing after a fixed and calculable date. It is an absolute terminus written into the value of a single parameter, currently being measured by satellites that are operational right now. The data from DESI and Euclid will not immediately resolve whether W is above or below -1. The measurements require years of accumulation and careful systematic analysis, but the trajectory of precision is clear, and within this decade, the constraints on W will tighten to the point where one scenario becomes significantly more probable than the other. The universe's ending, or at least the category of its ending, may be determinable from observations made within the lifetimes of people currently reading papers on dark energy. The Dark Energy Spectroscopic Instrument is currently measuring the parameter W with increasing precision. If its data confirms W is changing over time rather than fixed, what does that imply for every cosmological model built on the assumption of a constant cosmological constant, and how much of current theoretical cosmology would require reconstruction? However, both the Big Freeze and the Big Rip assume the universe continues expanding. There exists a third scenario once dismissed, and now partially rehabilitated, where the universe does the opposite, and it carries the strangest implications in all of cosmology. For most of the 20th century, the Big Crunch was the primary competitor to eternal expansion. The logic was straightforward and symmetric. If the Big Bang launched everything outward, gravity was the natural candidate to eventually reverse that motion. Given enough matter, the expansion would slow, stop, and reverse the universe, collapsing back toward a final singularity that mirrored its origin. A closed universe beginning and ending in the same mathematical condition, with the entire history of stars and galaxies and life compressed between two infinitely dense bookends. The scenario had aesthetic appeal. It was tidy. It respected the symmetry of the equations. And for decades, the question of whether the universe would expand forever or eventually recollapse was considered genuinely open, dependent on the total matter density, which was difficult to measure, precisely enough to settle the question. Then 1998 arrived, and the supernova data arrived with it, and the Big Crunch was effectively removed from the table. A universe with accelerating expansion cannot recollapse under gravity alone. The repulsive effect of dark energy overwhelms gravitational attraction at cosmological scales, and it does so with an increasing margin as the universe grows. With dark energy constant at its measured value, the Big Crunch requires either a fundamental misreading of the supernova data, which subsequent independent measurements have made increasingly implausible, or a dramatic change in the behavior of dark energy itself. That second possibility is what keeps the scenario alive. Dark energy is measured as a present-day value. The assumption that it remains constant in the future is exactly that, an assumption, not a derivation from first principles. Certain classes of dynamical dark energy models allow for a dark energy field that evolves over time, potentially weakening as the universe ages. If dark energy's repulsive effect declines sufficiently in the far future, gravity could eventually reclaim dominance. The expansion would slow, it would stop, it would reverse. The collapse would not be a gentle infall. As the universe contracted, radiation stretched to long wavelengths during expansion would be compressed back to shorter wavelengths and higher energies. The cosmic microwave background, currently a faint whisper at 2.7 degrees above absolute zero, would blue shift as the universe shrank, growing hotter and more energetic. Galaxy clusters would converge, galaxies would merge. Stars would be torn apart by tidal forces long before the final singularity, their material heated to temperatures exceeding those in stellar cores. The universe would return to a state of extreme density and temperature, a mirror image of its beginning, compressed in narrative from which the equations of general relativity, as currently written, cannot extract any further. Prediction: that is where standard Big Crunch cosmology stops. Singularity. End. The equations break down, and physics has nothing further to say. Roger Penrose does not stop there. His framework, Conformal Cyclic Cosmology, developed and published formally over the past 2 decades, proposes that what looks like a singularity at the end of one cosmic cycle is in the geometry of conformal mathematics, identical to the low entropy beginning of another. The technical argument involves a branch of mathematics called conformal geometry, which preserves angles and local shapes while allowing scale to vary freely. In conformal geometry, an extremely cold, dilute, expanding universe in its far future and an extremely hot, dense universe at its beginning share a mathematical equivalence that Penrose argues is physically meaningful rather than merely formal. The implication is that the endpoint of one universe, after all, black holes have evaporated after entropy has reached its maximum when only massless particles remain, drifting through an infinite cold expanse, transitions conformally into the initial conditions of a new universe. A new Big Bang, not a different universe collapsing and bouncing, but the same universe's endpoint becoming through conformal equivalence a new beginning. If this is correct, two consequences follow immediately. First, the question of why the Big Bang had such improbably low entropy has an answer. It was the necessary thermodynamic output of the previous cycle's endpoint, not a random initial condition selected from all possible states. The low entropy beginning is not a mystery requiring external explanation. It is a structural feature of how cycles connect. Second, the universe has no beginning and no end in any absolute sense. It has cycles. The question of what came before the Big Bang has the same answer as the question of what comes after the heat, death, another iteration of the same process. Penrose's framework makes a specific observational prediction. If previous cycles occurred, the collisions of supermassive black holes in the cycle preceding ours would have generated gravitational wave bursts that left imprints on the cosmic microwave background, concentric rings of slightly anomalous temperature around the points where those bursts originated. Penrose and his collaborators have searched the CMB data from multiple satellite surveys and reported finding patterns consistent with these rings. The scientific response has been divided and divided seriously. Several independent groups analyzed the same CMB datasets and reported finding no statistically significant ring patterns above what random noise would produce. The disagreement is not about the quality of the data. Both sides are using the same maps from the same satellites. It is about the statistical methodology, how ring patterns are defined, how background noise is modeled, and whether the detection thresholds applied by Penrose's group are appropriate. As of now, the claimed evidence is contested and has not been independently confirmed to a standard the broader cosmology community accepts. The philosophical consequences of a cyclic universe deserve direct attention because they reframe every question raised in this story. If cycles are real, entropy is not a one-way journey toward a final death. It is a reset mechanism. The universe does not run down permanently. It runs down to a state that generates new initial conditions. The arrow of time is local to each cycle, not a feature of a universe with an absolute beginning and end. This creates an immediate paradox regarding information. Every known law of physics suggests information is conserved, that the quantum state of any system is in principle recoverable from its future states run backward. If the universe cycles through singularities, and singularities are points where the equations break down, it is not clear whether information survives the transition. If it does not, each cycle begins fresh, with no causal connection to what came before. If it does survive in some form, encoded in the conformal structure Penrose describes, then each universe inherits something, perhaps not specific content, but structural constraints from its predecessor. Whether any information survives a big bounce is not a question current physics can answer definitively. The tools to probe what happens at or through a singularity do not yet exist, and developing them requires a complete theory of quantum gravity, the unification of general relativity, and quantum mechanics that has been the central unsolved problem of theoretical physics for nearly a century. If the universe is cyclic, and each big bounce resets entropy to a low initial value, does the concept of time having a beginning or an end retain any physical meaning, or does cyclicity make those concepts as geometrically meaningless as asking what lies north of the North Pole? All three scenarios, Big Freeze, Big Rip, and Big Bounce, share one foundational assumption that the universe under discussion is all that exists. Theoretical physics now has serious mathematical reasons to doubt that assumption, and the consequences of abandoning it change every question that has been asked so far. Cosmic inflation was not invented to create a multiverse. It was invented to solve three specific problems with the standard Big Bang model problems that were real quantitative and not otherwise resolved. The first was the flatness problem. Measurements of the geometry of the universe show it to be spatially flat to extraordinary precision. The total energy density is almost exactly at the critical value that produces flat geometry, rather than the positively curved geometry of a closed universe, or the negatively curved geometry of an open one. In the absence of some mechanism enforcing flatness, this requires the initial conditions of the universe to have been fine-tuned to a precision of roughly 1 part in 10 to the power of 60. Without explanation, this is as statistically uncomfortable as the low initial entropy. The second was the horizon problem. The cosmic microwave background has the same temperature in every direction to 1 part in 100,000, including regions of the sky that under standard Big Bang expansion could never have been in causal contact with each other. They are too far apart for light to have connected them in the time available, yet they share the same temperature. Something must have connected them before they separated. The third was the absence of magnetic monopoles. Certain symmetry-breaking transitions in the early universe, predicted by grand unified theories, should have produced exotic particles called magnetic monopoles in enormous quantities. None have ever been observed. Inflation solves all three simultaneously. Proposed by Alan Guth in 1980 and developed extensively in subsequent decades, the theory posits that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang expansion. So rapid that a region smaller than a proton inflated to a size larger than the current observable universe in roughly 10 to the negative 32 seconds. This expansion diluted any initial magnetic monopoles to undetectable density, stretched any initial curvature to flatness, and allowed the entire observable universe to originate from a region small enough to have been in thermal equilibrium before inflation began, explaining the uniformity of the microwave background. The inflationary model fits the observational data well. The small temperature fluctuations in the cosmic microwave background, the seeds that grew into galaxies, and the large-scale structure of the universe match the spectrum predicted by inflation with a precision that competing models struggle to replicate. The multiverse was not the goal. It was the mathematical consequence that came with the solution whether wanted or not. The mechanism that drives inflation is a field, the inflaton field, whose energy density temporarily dominates the universe and drives exponential expansion. Inflation ends when the inflaton field decays, releasing its energy into the particles and radiation of the hot Big Bang. But the quantum mechanics of that field do not allow it to end everywhere simultaneously. In any region where quantum fluctuations push the field's value upward, inflation continues. In regions where it decays, inflation ends, and a bubble universe forms. The inflating regions expand so rapidly that they always generate new inflating space faster than they convert it into bubble universes. The result is eternal inflation, a process that once started never globally stops. Our universe is one bubble where inflation ended approximately 13.8 billion years ago. Surrounding it and surrounding every other bubble universe that has formed is an inflating background that continues generating new bubbles indefinitely. The bubbles do not interact. They are separated by exponentially expanding space that prevents any causal contact between them. Each is effectively its own universe, with its own history, potentially its own physical constants, determined by how its local inflaton field decayed. The multiverse that emerges from eternal inflation is not a speculative addition to the model. It is a direct mathematical output of the same mechanism that produces inflation's observational successes. Accepting inflation's explanation for the flatness horizon and monopole problems while rejecting the multiverse requires finding a reason to stop the mathematics partway through a reason that does not currently exist. This creates a significant scientific discomfort. The other bubble universes are not merely distant. They are causally inaccessible by construction separated by expanding space that no signal can cross. No observation from within our bubble universe can directly detect the existence of another bubble. The multiverse makes no prediction that if falsified would rule it out. Several physicists, including David Gross and Paul Steinhardt, both serious figures with major contributions to theoretical physics, have argued that a framework incapable of producing falsifiable predictions falls outside the boundaries of science as currently defined and should be recognized as metaphysics expressed in mathematical language. The counterargument is that certain inflationary models do make predictions testable within our observable universe. Primordial gravitational waves, ripples in space-time from the inflationary epoch, would leave a specific polarization signature in the cosmic microwave background. Detection of that signature would support inflation strongly, though not uniquely confirm the multiverse. Additionally, if our bubble universe collided with another during the inflationary period, the collision would leave a specific imprint in the CMB. Such signatures have been searched for and not found, but not finding them does not definitively rule out bubble collisions, since the geometry of any collision depends on circumstances that may not have produced a detectable imprint in our sky. The anthropic principle enters here directly. If physical constants vary across bubble universes, the question of why our universe has the specific constants it does, including the value of dark energy, which is smaller than theoretical calculations predict by a factor of 10 to the player. The power of 120 receives a statistical rather than a causal answer. We observe constants that permit complexity and life, because universes with different constants have no observers to note their properties. The selection effect is real. Whether it constitutes an explanation or merely restates the observation in probabilistic language is a question on which physicists hold genuinely different views. What the multiverse framework does to the question of cosmic endings is structurally significant. The Big Freeze, Big Rip, and Big Bounce describe the fate of this bubble universe, this particular region of space where inflation ended 13.8 billion years ago. If eternal inflation is real, the process generating new universes continues regardless of what happens here. Our universe ends. The multiverse does not end. The concept of a final state for all of existence loses its referent. If the multiverse cannot be directly observed or falsified by any conceivable experiment conducted within our universe, does accepting it as a physical reality require a revision of what science means by explanation, or does it simply represent a legitimate extension of scientific reasoning into Thule domains where direct confirmation is structurally impossible? But even without a multiverse, even within the boundaries of this single universe, there exists a threat that has not yet been named in this story, quieter than the Big Rip, more certain than the Big Bounce, and possibly already underway right now, with no warning of any kind. Everything discussed so far assumes the universe is operating correctly, that the physical laws governing matter and energy are stable, that the constants underpinning chemistry and atomic structure will remain what they are, that the ground beneath all of physical reality is solid. The Big Freeze, the Big Rip, the Big Bounce, all three assume the rules stay fixed while the game plays out to its conclusion. That assumption may be wrong, not in a speculative philosophical sense, in a precise calculable quantum mechanical sense that follows directly from a measurement made at the Large Hadron Collider in 2012. To understand why it is necessary to understand what the Higgs field actually is, and what it does not as an abstract concept, but as a physical property of the vacuum itself. Empty space is not empty. This is one of the most consistently misunderstood results of quantum field theory. What appears to be a vacuum, a region containing no particles, no radiation, no matter of any kind, is actually a seething substrate of quantum fields, each permeating all of space and each existing in some energy state. The Higgs field is one of these. Unlike most fields, whose lowest energy state corresponds to a field value of 0, the Higgs field has a lowest energy state at a non-zero value. It is switched on everywhere in the universe all the time at a specific constant value. That value is what gives particles mass through their interaction with the field. Without it, electrons would have no mass, atoms could not form, chemistry would not exist. The critical question is whether the current value of the Higgs field corresponds to the true lowest energy state, the absolute ground state stable against any perturbation, or whether it corresponds to a local minimum in the energy. Landscape, a bowl-shaped depression that looks like the bottom, from inside but sits at a higher energy than a deeper basin located elsewhere in field space. In physics, the first case is called a stable vacuum. The second is called a metastable vacuum, or false vacuum. A marble resting at the bottom of a bowl represents a stable vacuum. Any perturbation causes it to roll back to center. A marble resting in a shallow depression on the side of a hill represents a false vacuum. It appears stable under small disturbances, but given enough energy to escape the depression or through quantum tunneling without needing any energy all it will roll to the true bottom. Quantum tunneling is the mechanism that makes false vacuum decay genuinely threatening rather than merely theoretical. In classical physics, a particle trapped in a local energy minimum cannot escape without acquiring enough energy to climb over the barrier. In quantum mechanics, particles have a calculable probability of passing through barriers without climbing over them, tunneling directly from one side to the other. For macroscopic objects, tunneling probabilities are so vanishingly small they are irrelevant. For quantum fields permeating all of space, the calculation is different. In any sufficiently large volume over sufficiently long timescales, a quantum fluctuation can nucleate a bubble of true vacuum, a region where the Higgs field has tunneled to its actual lowest energy state. Once nucleated, that bubble expands. The true vacuum has lower energy than the false vacuum surrounding it, and the energy difference drives the bubble wall outward at the speed of light. Inside the bubble, the Higgs field has a different value. The masses of all elementary particles are different. The electromagnetic force, the strong force, the weak force, all governed by constants that depend on the vacuum state, take different values. Chemistry, as it exists in our universe, is impossible inside the bubble. Atoms cannot form. Molecules cannot exist. Any structure more complex than bare quantum fields is immediately and completely eliminated as the bubble wall passes through it. The wall arrives at the speed of light. No signal can precede it. No warning is possible. An observer in the path of an expanding true vacuum bubble would have no indication, no premonition, no final moment of awareness. The bubble wall is not a wall of energy or radiation that can be detected at a distance. It is a boundary where the rules of physics change, and it moves at the maximum speed at which information can travel. The region behind the wall has simply become a universe, where the things that existed in front of it are not possible configurations of matter. Physicists describe this scenario as the most comfortable of all possible catastrophic endings. Not because it is pleasant, but because no suffering is involved. The transition from existence to non-existence happens faster than any physical process in a nervous system can complete. This is a notably specific definition of comfortable. It says more about the range of options being compared than it does about the scenario itself. Whether the universe is stable or metastable depends on the mass of the Higgs boson and the mass of the top quark, which together determine the shape of the Higgs field's energy landscape. The Large Hadron Collider announced the discovery of the Higgs boson in July 2012 and measured its mass at approximately 125 giga-electron volts. When that value is combined with precision measurements of the top quark mass, the calculation of vacuum stability places our universe in what physicists describe as the metastability region. Not clearly stable, not clearly unstable, but sitting close to the boundary between the two. The boundary itself carries significant uncertainty. The mass measurements involved have experimental errors, and the theoretical calculations relating those masses to vacuum stability involve approximations whose corrections could shift the conclusion towards stability or deeper into metastability. As of current measurements, the most precise analyses place the universe in a region where stability cannot be confirmed, but where the probability of vacuum decay within the current age of the universe is extremely small. The timescale for spontaneous nucleation of a true vacuum bubble, if the universe is indeed metastable, is estimated to be vastly longer than the current age of the universe. Cosmological timescales vastly longer, in ranges that dwarf even the black hole evaporation timescales discussed in Part 6. The unsettling addition to this picture is observational rather than theoretical. If false vacuum decay has already occurred somewhere in the universe, and the universe is large enough, old enough, and the nucleation probability per unit volume, per unit time is non-zero, which it is. If the vacuum is metastable, then a bubble is expanding somewhere right now. Possibly many bubbles. The question of whether one is currently on a trajectory toward our location cannot be answered by any observation, because the only signal traveling from the bubble's origin is the bubble wall itself moving at light speed. If a vacuum decay event occurred 10 billion light-years away 10 billion years ago, Its bubble wall is 10 billion light-years across and has been expanding for 10 billion years. There is no advance notice. There is no electromagnetic signal, no gravitational wave, no neutrino flux that outruns it. The first indication of its existence would be simultaneous with the last moment of anything in its path. This is not a statement about probability. The probability of vacuum decay in any given region of space per unit time is calculated to be extraordinarily small. It is a statement about the structure of the threat. Unlike every other cosmic danger, it cannot be characterized, monitored, predicted, or avoided by any conceivable technology. It is the only scenario in the catalogue of cosmic endings that is simultaneously physically grounded, potentially already in progress, and absolutely opaque to observation. If false vacuum collapse cannot be detected, predicted, or prevented by any physical means, does it qualify as a scientific question in the meaningful sense, or does its complete unobservability place it in a category that requires a different framework than empirical science to address? The most paradoxical aspect of all these scenarios is that they are being studied by creatures that emerged from the very imperfections of the universe they describe. And the final question is not which scenario is correct, but what happens to information when the universe ends. Every scenario described in this story ends with the same implicit assumption that when the universe reaches its final state, whether through thermodynamic exhaustion, structural tearing, cyclic collapse, or instantaneous vacuum decay, whatever existed within it is simply gone. Matter disperses or is destroyed. Energy dilutes to uselessness. Complexity dissolves. The universe arrives at a state in which nothing of its history remains in any recoverable form. Quantum mechanics says this cannot happen. This is not a philosophical objection or a statement about the resilience of information in a practical sense. It is a foundational claim of quantum mechanical theory, encoded in the mathematical structure of how quantum states evolve over time. The evolution of a quantum system is governed by a unitary process, a transformation that is by construction reversible. Given the final quantum state of any system and the laws governing its evolution, the initial state can be reconstructed. Information, the full specification of a system's quantum state, is conserved. It cannot be created from nothing, and it cannot be destroyed into nothing. It can only be transformed, scrambled, redistributed across degrees of freedom in ways that make it practically inaccessible, but never genuinely erased. This principle has survived every experimental test in the history of quantum mechanics. It is not a conjecture or an approximation. It is structural. Black holes violate it, or appear to. The apparent violation was identified by Stephen Hawking in the same 1974 paper that predicted black hole evaporation. The argument runs as follows. When matter falls into a black hole, the information specifying its quantum state, the precise configuration of every particle, every field value, every quantum number, falls in with it. That information crosses the event horizon, the boundary beyond which nothing returns. It is, from the perspective of an outside observer, completely inaccessible. The black hole retains only three externally measurable properties: mass, electric charge, and angular momentum. Everything else about the infalling matter is hidden behind the horizon. As the black hole evaporates through Hawking radiation, it gradually loses mass and eventually disappears. The radiation it emits during evaporation is, in Hawking's original calculation, perfectly thermal, randomly distributed in energy, according to the temperature of the black hole, with no correlation to the specific quantum state of the black hole, matter, that fell in. When the black hole has completely evaporated, the information about everything that ever fell into it is simply absent from the final state. It has been destroyed. If that conclusion stands, quantum mechanics is wrong at a fundamental level. Unitary evolution, the core of quantum theory, is violated. The reversibility that the mathematical structure demands has been broken. The alternative is not more comfortable. If the Hawking radiation must somehow encode the information about infalling matter, if unitarity is to be preserved and quantum mechanics is to remain valid, then the radiation cannot be purely thermal. It must carry subtle quantum correlations corresponding to the quantum state of the infalling matter. For that correlation to exist in the radiation, the outgoing particles must be quantum entangled with something at or near the event horizon. But general relativity, as Einstein formulated, It makes a specific prediction about the event horizon. It is locally unremarkable. An observer crossing it experiences nothing special, no wall, no barrier, no physical event marking the transition. The horizon is a global feature of the space-time geometry, not a local physical boundary. If the Hawking radiation must be entangled with something at the horizon to preserve information, that entanglement requires the horizon to be a physical structure of some kind. What theorists, after a 2012 paper by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully called a firewall, a boundary of high-energy radiation at the event horizon that destroys anything crossing it. This resolves the information paradox by preventing information from ever truly entering the black hole in an inaccessible form. But it directly contradicts general relativity's prediction that horizon crossing is locally uneventful. The two pillars of modern physics, quantum mechanics and general relativity, are in direct, unresolved conflict at the event horizon of every black hole in the universe. The conflict has been known in various, it has not been resolved. The most mathematically developed proposal for resolution is the work of Juan Maldacena, published in 1997, known as the AD-S CFT correspondence. This framework establishes a precise mathematical equivalence between a theory of gravity in a particular type of curved spacetime and a quantum field theory without gravity on the boundary of that spacetime. In this correspondence, black hole physics in the interior is exactly dual to a quantum field theory on the boundary, and quantum field theories are unitary. Information is preserved on the boundary, which means through the equivalence, it is preserved in the bulk with the black hole. The correspondence provides strong mathematical evidence that information is not lost in black holes, that the apparent destruction is an artifact of describing the physics in the interior without access to the complete boundary. Description: the information exists. It is encoded in the Hawking radiation in correlations so complex and spread across so many degrees of freedom that recovering it is for any practical purpose impossible. But it is there. The implication for cosmic endings is structural. If information cannot be destroyed if unitary evolution holds globally, then even in the most complete cosmic ending imaginable, the information content of the universe is not eliminated. In the Big Freeze, it is maximally scrambled across the lowest energy photons and particles drifting through cold space, inaccessible but present. In the Big Rip, the question of where the information goes when spacetime itself tears is precisely the question that requires a theory of quantum gravity to answer, and that theory does not yet exist. In false vacuum decay, the bubble wall changes the rules of physics inside it, but whether the information encoded in the quantum fields it replaces is genuinely destroyed or transformed into the new vacuum's degrees of freedom is an open problem. The universe may not be capable of truly dying in the informational sense, regardless of what happens to its matter, its energy, or its space-time geometry. What death means for a quantum system with conserved information is a question that none of the scenarios in this story have answered. If information cannot be destroyed even inside a black hole, and black holes encode all infalling information in their Hawking radiation, in principle, does that mean every event that has ever occurred in the universe is in principle recoverable from the final state, and what would it mean for physics? If the answer is yes, this is the point where physics and philosophy make contact, and that point of contact contains the final question. The one that none of the cosmic scenarios above actually answer. Pull back from all of it. The entropy, the expanding horizon, the phantom energy, the firewall, the false vacuum, the infinite bubbles. Pull back far enough to see the full shape of what has been described across this story, and a single, uncomfortable fact emerges with clarity. The universe is dying by entropy, that much is certain, written into the second law with no exceptions and no appeals. Beyond that certainty, the specifics fracture into contested territory. Dark energy may be constant, leading to a cold and silent thermodynamic death across timescales that make the current age of the universe a negligible opening. It may be strengthening, in which case the fabric of spacetime itself tears apart at a calculable date, and everything from galaxy clusters to atomic nuclei is shredded by the expansion of space before entropy ever finishes its work. It may weaken and reverse, allowing a collapse back towards singularity, and that singularity may be a true ending or a transition into a new cycle, depending on whether Penrose's conformal equivalence holds. The universe may be one bubble among an uncountable number, making the concept of a final state for all of existence geometrically meaningless. And underneath all of it, the ground state of reality itself may be a metastable configuration waiting to tunnel to a lower energy, a process that could have already started somewhere in the observable universe with the evidence traveling toward us at the speed of light, indistinguishable from the absence of evidence until the moment it arrives. 5 scenarios, each grounded in real physics, each supported by some combination of theoretical framework and observational evidence, each leading to a categorically different kind of ending, and current science cannot determine which one describes the universe we actually inhabit. That is the honest summary. But it is not the most important thing to say here. The most important thing is that the uncertainty is shrinking, and shrinking at a pace that has no precedent in the history of cosmological science. The dark energy spectroscopic instrument is operational now, mounted on the Nicholas U. Mail telescope at Kitt Peak Observatory in Arizona, measuring the redshifts of tens of millions of galaxies across 11 billion years of cosmic history. When its 5-year survey is complete, its constraints on the parameter W, the ratio that determines whether dark energy is constant, weakening, or strengthening, will be more precise than all previous measurements combined. The first data release in 2024 already hinted at possible evolution in W. The full dataset will either sharpen that hint into a signal or dissolve it into noise. Either answer is definitive in a way that no previous measurement has been. The Euclid satellite, launched by the European Space Agency in 2023 and currently mapping the shapes and positions of billions of galaxies across the past 10 billion years, will add a complementary constraint through weak gravitational lensing, the subtle distortion of distant galaxy images by intervening matter. Euclid's dark energy measurements are independent of DESI's in methodology, which means agreement between them will be far more convincing than either alone. Disagreement will identify systematic errors. Either outcome advances understanding. The Vera C. Rubin Observatory in Chile, entering full operations with its legacy survey of space and time, will identify hundreds of thousands of Type Ia supernovae over 10 years, the same class of stellar explosion that revealed accelerating expansion in 1998, now measured at vastly greater numbers and precision. The Hubble tension, the persistent disagreement between different methods of measuring the universe's current expansion rate, may be resolved by this data, or may deepen into evidence that the standard cosmological model requires. Structural revision, CMB, S4, the next generation of cosmic microwave background experiments, will search for the primordial gravitational wave signal that inflationary models predict. Detection would strongly support the inflationary framework and by extension make the multiverse hypothesis considerably more serious as a physical proposal. Non-detection at CMB, S4's sensitivity level, would rule out the simplest inflationary models entirely and force a reconsideration of the mechanism, explaining the flatness and horizon problems. At the Large Hadron Collider and its planned successors, precision measurements of the Higgs boson mass and the top quark mass will continue to sharpen the calculation of vacuum stability. The next generation of colliders, currently in planning stages, would measure these parameters with sufficient precision to determine within the theoretical uncertainties of the calculation whether the universe sits in a stable or metastable vacuum state. That determination will not tell us whether false vacuum decay is occurring somewhere right now. The observational opacity of that scenario is absolute, but it will tell us whether the threat is real in principle, which is the only question physics is equipped to answer. What will not change regardless of which scenario the data selects is the structure of the situation that produced these questions. The universe began in a state of entropy so extraordinarily low that its probability is a number without a name in mathematics. It has been spending that initial order for 13.8 billion years, producing in the process stars' heavy elements, planets, chemistry, biology, and eventually nervous systems complex enough to represent the universe's own history to itself. The window during which this kind of complexity is possible is narrow, bounded at one end by the universe, being too hot and too dense for stable structures, bounded at the other end by the exhaustion of stellar fuel and the dissolution of the conditions that make chemistry work. The entire span of human civilization, from the first controlled use of fire to the construction of telescopes capable of reading the universe's expansion history, occupies a fraction of that window so small it has no intuitive a log. In that fraction, enough was learned to outline what comes next. Not in every detail, not with certainty about which specific ending applies, but in broad enough terms that the shape of the future, long or short, cold or torn, cyclic or terminal, is no longer completely unknown. The instruments running right now will narrow the remaining uncertainty within this decade. The data being collected tonight at observatories across Earth and in satellites currently in orbit will, when analysed, push the probability of each scenario further from or closer to the conclusions current measurements suggest. For the first time in the history of any known civilization in the universe, a species is close to knowing how the universe it lives in ends before it ends. The surveys are running, the data is coming in, and the answer, whatever it turns out to be, will arrive not from philosophy, not from conjecture, not from the kind of reasoning that fills the gaps between measurements with preferred assumptions. It will arrive from instruments pointed at the sky, accumulating photons that carry the universe's own account of where it is going. The universe has been moving in one direction since the beginning. Now, for the first time, something inside it is watching closely enough to read the destination.